So, hi everybody. I'd love to introduce Amos Golan from the American University in Washington, where he studies informatics, which is kind of the broadest level of our understanding of information and dynamics. Welcome.
Thank you, Greg. Just make sure you hear me fine, everyone.
Yep.
Okay. Thank you, Greg. I'm delighted to be here, and I like your talk series. I'm going to talk today about information theory and modeling and inference in general. Basically, the world is complex, and the observed information that we have for modeling and inference is quite complex as well, especially in the social and behavioral science, though the same hold in most of the natural sciences as well, to my understanding. But even more important is that we never have sufficient enough information to do perfect modeling. We never have all the information that we need for modeling in inference. In fact, we always have insufficient. What it means basically that all problems, modeling, inference, solutions, if you wish, are underdetermined. They are subject to multiple solutions that are fully consistent with the observed complex or less complex information that we have. So to overcome this problem, what we usually do in science is we assume some structure and assumption that very often we cannot really validate. In my talk today, I'm going to discuss a different approach. I'm going to talk about information-theoretic approach for dealing with such underdetermined problems in general. It complements the other approaches, and it is based on the minimally needed information in order to do inference. There are no hidden assumptions. All information that is used is accounted for. It doesn't mean that it's always the correct information, but at least we know all of the information that we use in the model that we develop or in the inference that we do, conditional on some data. One can think about it as the least bias modeling approach, because basically what it does, it accounts for all of the information. So it's not biased by implicit and unknown or unobserved information in the model itself. Though each problem is specific, I'm going to talk about a framework and for doing this type of analysis, which I call informatics. I will present the basic idea, the basic philosophy of the basic idea, and then I will provide some empirical evidence. The basic idea I will present via a number of pictures and figures that can present the problem and the underlying theory, and then I will generalize it to the case where I will start with a simple problem, and then I will generalize it to the case where we have a lot of uncertainty. You can think of uncertainty as the classical uncertainty, misspecification, because we never really know the exact underlying theory, and what is called in the classical statistical and econometric literature model ambiguity, because we're uncertain about the model. So we have to allow for some model ambiguity and uncertainty. So this is the outline of the talk and the basic objective of what we want to do. Again, I want to present the basic theory via a simple, very simple example, but I think it captures everything that we want to talk about. So the basic idea is we want to model. The system that we usually want to model are complex system. I mean, life is nonlinear. Data are nonlinear, so we have to take it into account. So we need to do also either modeling, pure modeling, based on some axioms or what we think we know. Same thing when we do inference, then we face complex data because it emerges from some complex evolving systems. Examples are, there are many examples, but what I wrote here economics, ecology, biology, and of course, many other systems. We never have all the information that we need. And even if theoretically we would have infinitely much information, we can't handle it in finite time. But the truth is that we don't really have all of the information that we want. So then we have multiple solutions. So the problem is underdetermined. One possible solution, the one that I will talk about today, is rather than what there are other possibilities. One possibility, of course, is to impose structures or assumptions, but good luck verifying those assumptions. Other possibility that I'm going to talk about it is to think about the problem, to convert this underdetermined problem into a simple constraint optimization. All the information that we have, hard data, which is the data, or hard information, think about it is the data, the numbers that we observe, the observed information, including that could be assumption, conjectures, whatever we want to do, things that we believe we know, and then we can validate. Those will be the constraints. And then, of course, we have to choose a certain decision function. It's clear from the title of this talk that the decision function I will use here, and that it's based on some axiomatic derivation and so on, is coming from information theory, and basically it is the Shannon entropy. There are other entropies, but I'm going to talk about Shannon entropy. I'm going to talk later on about some other entropies, just in order to show how this basically can be generalized to include all of the possible statistical methods that people often use. Okay, so basically, I like to think about it that information theory brings a lot to the table, and now I'm going to show what, to me, it brings to the table. But first, let's think about it, the basic issue. The basic issue here, we have multiple problems with multiple solutions, say x plus y equals 10. Okay, give me one more piece of information and we have a perfect solution. But what if I tell you that the real problem in life is x plus y equals more or less 10? The more or less, think about it, would mean zero noise. The more or less captures some of the uncertainty. Then it means that basically, if you think about it, it's not a data size issue. It's a fundamental issue due to the ambiguity, due to the uncertainty that is in the information that we have. Because with x plus y equals more or less 10, as you can add a lot of additional pieces of information. You know, y minus x equals more or less 5, and so on and so on. But it's more or less, so it will converge to the truth maybe, but in infinitely long time. So, and this is basically what we're facing. So we're putting it as a constraint optimization. I'm going to start with the constraint. The constraints are the information that we have. Okay, think about it as conservation law, or basically the information that we have. Think about it, those are the rules that governs the behaviors of those complex systems or less complex systems that we try to understand. Those are the rules that govern the behavior of the system. So those are basically the constraints. It's all the information that we have. Now, the constraints are really hard to specify, and it's problem specific, but now I'm going to talk about it in more general terms, and then we move into some specific examples. So those are the constraints. Of course, if we deal with probability distribution, we have to have normalization. Now, the idea here is that just using this information, this will still be underdetermined. So we have to have a certain function or decision function, or economists will call it utility function or preferences. However, it is this decision function that will choose one of the infinitely many possible or multiple possible solutions that are consistent with the information that we have. Okay, so this is the basic idea, and the decision function I'm going to use here will be Shannon's entropy. Of course, there are many others. There could be a likelihood function that we all are familiar with, could be least square, For some, could be what is known empirical likelihood, and there are many other types of decision function. So the question that we have when we try to model a problem is what information we have, what do we think we know about the system that we're pretty certain about, because constraints have to be satisfied in a constraint optimization. And we have to choose a decision function. Often we also have priors, which is something that I will ignore in this talk. We just don't have enough time, but priors are something that come from outside the system, either from some logical or theoretical arguments from outside the system, or it could come from another system, from another data set. It's something that can think about it as a characteristics of all of the entities in the population that we try to understand or to model. Okay, so this is the basic idea of converting the problem from a multiple solutions underdetermined to a well-behaved determined. Because if you have a well-behaved objective function, that it's trivial to argue that basically if you put it as a constraint optimization, then this decision function choose a unique, if it's well-behaved, a unique solution. So this is the basic idea here. It's true, and it's a side comment, that there are other approaches within statistics econometrics to do it, where they want to look at all of the multiple solutions. But then, of course, it depends on the specific problem, and then it becomes not more complicated, but then we have multiple solutions, and again, we will have to think which one to accept. But this takes us to a different problem. So back to this problem. Yeah.
So question for your, I guess, philosophical approach, because at a high level, it's all the same family. You have, well, these constraints and you optimize given them, and your philosophy seems to be Occam's razor. Find the, Shannon entropy, simplest solution that is consistent. Except you also have constraints like conservation laws that come from outside of information theory. So what's this? And it seems like econometrics leans heavily into these outside constraints, and is your approach just simply to lean lightly and use information theory as your fundamental core?
Yes, it's a perfect question. The constraints are not to do with information theory. The constraints are what I think the information that I have. It could be hard data information that I observe, but it also could be my what I call here the soft information. It could be what I believe is are the rules that governs the behavior of this system. But the advantage here is that then I can test it statistically as well. But indeed, you touch on the most important issue, is that the constraints are the toughest thing. It's just like a functional form in any modeling is the toughest thing to come by, because it's not trivial. We have to understand the system that we're dealing with. So I'm not sure if I answered. Yeah, go ahead.
Well, no, you did. And then the follow-up really is, where do they come from? How do you currently, and this is the trickiest thing, but do you currently have a way of accounting the evidentiary base for prior knowledge? Or do you just say, I assume this, and future work traces evidentiary bases across studies?
Okay, so it comes from our understanding of the system that we try to model. Then within this approach, we can also test the assumptions or the structure if it is consistent with the observed data that we have. We'll see later on some example. So the constraints can be tested against the data that we have. This is in the more empirical way. Other than this, basically you impose constraint that you believe, basically capture the underlying theory, and then you do the optimization, you get your solution, and then you look at it and you try to figure out whether it behaves as you think it does, or it behaves very different, and then you try to adjust the constraints accordingly. So the choice of the constraints is the main problem always. But I'm going to talk now about the overall framework, and I'll show some examples later on of specific empirical cases where the constraints are determined based on some outside knowledge.
Okay, great. Thank you.
Sure. So now I want to demonstrate the idea in the simplest dimension that I can, also dimension that I can put pictures. So think of rather than a six-sided die, it's hard to put pictures of the six-sided die. Think of a three-sided die, and you play the three-sided die a number of games, let's say n games, okay? And at the end, the only information that you have is the mean value, which has to be something between 1 and 3. So let's say you have a three-sided die, like in this picture, with three numbers, 1, 2, and 3. And after n games, then somebody tells you the mean. Let's say the mean is 1.5, or the mean is 2, or the mean is 2.02. And based on this, you want to bet on the next toss of the die, the three-sided die, or you just want to infer the probability distribution of this die and to see whether it's fair or if it's a biased die. Very simple problem, but we'll see later on that it generalizes to almost all problems within modeling and statistics. Okay, so what is the observed information that we have? We have the empirical mean. We don't know the frequencies. We just know that's the rules of this game. We just have the mean and the normalization. So we have two pieces of information. We want to infer the probability distribution, probability of observing 1, 2, or 3. So we have three unknowns and we have two pieces of information. So we know that we have multiple solutions. So now let me show it graphically. So bear with me here. I'm going to start with this. It's a simplex. So this is the description of the problem. Okay, and then later on we'll come to the solution. So this is a simplex. Think of this as problem in the bottom left. I call it V sub B. It's 1, 0, 0. So those triplets are the values of the probabilities. So the probability here is 1 on 1, 0 on 2, and 0 on 3. And here it's the second triplet. It's on the number 2, 0, 1, 2. So the second value is probability of 1 on 2. And this is probability of 1 on 3. And this creates a simplex in a way such that every point inside the simplex, or on the boundary of the simplex, is equal to the sum of equal points. Sorry, every point in the simplex, or on the boundary, is a normalized probability distribution, meaning that on every point here, P1 plus P2 plus P3 equals to exactly 1. Okay, so for example, here we have that we see that P1 equals to 1 and the other two equal to 0. And think about it, how we're measuring the value of the probability, or the normalized value. Basically, it's the distance from the point all the way, think about it, 90 degrees here to the other side. So this is a distance of exactly 1. So here it means that the value, the probability of 1 is 1 and all the other is 0. Here it's exactly different. It's the distance from here. So this will give a probability of 1 on 2 and 0, probability of 0 for 1 and 3. And the same thing here for 3, probability of 1 on 3. This is the value for 3. And this is the three-sided die. The top face is 3, and it's a probability of 1 on 3. And of course, every point in between. For example, in this point here, you can see that this is P2 because it's closest to to 2. So this is P2, which is the larger, which is greater than P1, greater than P3. Okay, because on this point, on this line, basically all of the probability of P3 are exactly 0, because remember, this is the distance to P3. And this is the center of gravity where all of the probabilities are equal. 1/3, 1/3, 1/3. Okay? So this simplex basically, so everything has to happen within the simplex in this problem. Because remember, we have a piece of info, we had 2 pieces of information that we observed. One is the normalization. This is what we talked about. Outside this simplex, the probabilities don't sum up to 1. So nothing can happen outside this simplex. Okay. So now we have basically a definition of the simplex. Economists in general are familiar with the idea of the simplex because for economists, prices are normalized and can always put within a simplex. But this is just a 3-dimensional simplex for the probability distribution. Okay. Forgot to mention in questions, just let me know or stop me. I won't see messages. Okay, next is we want to talk about the other constraints, the informative constraint, the mean value, the expected value. So let's see how we think in this problem of the expected value. Remember, this is the second piece of information. We said that the expected value has to be it's between 1 and 3, and we know the expected value. So let's start at this point. Okay. So at this line here, sorry. So at this line here, we see that the probability of 2 is 1, so the expected value here must be 2. Here, the probabilities, because at this point here, remember, over this boundary line here of the simplex, all of P2 must be equal to exactly 0. So at this point here, we have P1 equals to 1/2, P3 equals to 1/2. So the mean value has to be equal to exactly 2, correct? P1, so it's 1/2 times 1 plus 1/2 times 3 gives us exactly 2. And because we define the problem as just the mathematical mean, the arithmetic mean, there are other means, I'll touch on it later on if we have time, but here it's just the arithmetic mean, so it's linear. So then it means that all those lines, all those points on this line that goes from here, from 1/2 on 1 and 1/2 on 3, all the way to probability of 1 on 2. So every point, okay, on this line has a mean of 2. So now we understand the problem. So now we have the problem of, okay, which solution should we choose? Because we have infinite, assuming if the observed mean values after n games is 2, then each one of those could be, or these points here on this line, infinitely of this, can be the solution. Okay, now let's choose another number. So this will be a number with a mean value above 2, because we're getting close to the 3 here. So this is mean value above 2, let's say 2.5. So every point on this line will be 2.5. Again, which one should we choose? And similar here, all of those points below and to the left of the 2 will have a mean value that is less than 2, for example, 1.5. Okay, so which point should we choose? Okay, so now we describe the problem and we see the 2 constraints. So remember, each point on this line satisfies both of our pieces of information. It satisfies the normalization, the probability sum up to 1, and it also satisfies the constraint that the mean value has to be exactly to 2. Now we have to make our choice. So to make our choice, we're going to use our decision function. So the decision function, I'm writing it here as the contour, or I call it the Shannon entropy contour. So let's start with this one. Each point on this contour here has equal entropy value. Okay. The same thing here. Each point on each one of those contour, or you can call it indifference curve, it means that all the points on this, and it's not a circle and it's not an ellipse, it's just the entropy function here. So each one here has exactly the same entropy level. So as you go toward the center of gravity, where all the probabilities are equal, you get the largest entropy. I'll define it in a minute. And you can see that each one of those entropy contours is represented by its boldness and darkness. So as you go far away, the entropy decreases. For example, here the entropy will be exactly 0, because here we come to a perfect certainty. It's at this point, for example, or this point, the entropy is 0 because there is no uncertainty. And Shannon entropy, basically, you can think about, represents something about the level of uncertainty. So the entropy goes from 0, perfect certainty, to perfect uncertainty at the level of uniform distribution. This is the uniform distribution, center of gravity, if you wish, where it just basically, if you think about it, it's just the entropy is log of k. In this case, it will be log of 3. Okay, so those are the contours. And what is the solution? The solution is, of course, the point where the contour or the indifference entropy curve here is tangent to the constraint, to the mean constraint. Okay. For example, if this is the mean constraint, then this here is the solution. So it's where so one is tangent to the other. So you can say, in other words, that the slope of this line and the slope at this point of the indifference curve are exactly the same. And the same thing here, and as we go along. And finally, this.
Do you mean tangent, or do you mean just crosses? Are we guaranteed there's a certain direction of cross?
They tangent to it. They touch each other in the same slope. So just think about it. You maximize say I'll show it in a bit, but you maximize the decision function subject to the constraint. So you form a Lagrangian, basically, and then the first order derivative, when you take the derivative, it will be equal to 0. So you can show that the slope here at this point will be equal to the slope of this line here. This is what I mean by tangent.
Interesting. Okay, cool. Thank you.
So, and this, I call it the locus of optimal solution. It means that for this, because it's a specific problem, for this specific problem with this structure of the constraints, the optimal solutions lies here. So, for example, if this is the if this would be the constraint here at like 2.7 or 7.5, then this would be the solution here. So the optimal solution falls on this locus of optimal solutions here. Okay, for this specific problem, it cannot be outside here. And when I say optimal, I mean optimal under Shannon entropy. I will show other examples later on when, of course, the solution will be different, because you have a different decision function. It will choose a different point. So this is the basic idea. And now I'll just briefly show it more mathematically. So let's start with the constraints. So the constraints here I wrote in general way. So those are some kind of moments. It could be in the mean, it could be any type of moment. So we have here m equals 1 to m different. You can think about it as moment or conservation rules. Okay. So it's just basically the simple mean. And I wrote here a function f sub m, meaning that it doesn't necessarily have to be linear, but of course, it could be linear as a special case. And those are the normalization. And of course, as we saw in the simplex, all the p's have to be non-negative and sum up to 1. But if we just use this, then we know that the problem is underdetermined because the number of m, which I apologize, I forgot to put here, the number of m is smaller than capital K with the number of elements in the discrete probability distribution of dimension K. In our case, it was 3. And in our case, m equals to 1. So you see that still we have less constraints than unknowns. And this is the definition of the discrete Shannon entropy. I didn't put log sub 2 here. It can go, so one can use any log that you want. Originally, it goes with log sub 2, so it has a meaning of bits of information. But for technical reason, or it's usually much easier to use here the natural log or ln. But as you know, it doesn't really matter what base log we use here. The solution with respect to the p's will remain the same. So this is the optimization problem. Those are, and now to solve it, basically, one follows the classical idea of Lagrange, the Lagrangian approach. So we form a Lagrangian, and then it means that we will have a Lagrange multiplier associated with each one of the constraints. So it will be m associated with this and 1 associated with the normalization. This is what I called here the lambda. And once we go through the derivation, we get the solution, which is the exponential distribution. Now, it depends on the f. If this function is linear, then it will remain exponential. If f, for example, is not linear, then it not necessarily will be exponential. But this is the overall functional form. And just for simplicity, I call this omega. This is called, and to relate it to the literature, in the more natural science literature or Bayesian, it will call the partition function. But if you look at this, basically, it's just a normalization factor. So it just normalizes everything that we have in the numerator to make sure that the p's are well-behaved normalized probability distributions that sum up to exactly 1. Okay.
So let me see if I can connect this to something else. So, I mean, a lot of this math looks a lot like Nash equilibrium kind of stuff, where I have a mixed random strategy, which is a linear combination, specifically linear combination, just like I saw you doing here, of very possible moves. And it's what is my, what my player's best strategy is the best solution here. Is that fair?
That's fair under certain conditions, yes. Yeah. Though, and I'll come because this is one of the examples I have, empirical. But remember that when you talk about game theory and game, it's a different. This is a top-down approach. Game theory in economics is a down-up because you start with the assumption on the rationality and the behavior of the individuals, and then from there on, you come up to equilibrium. Here, you don't have to assume those. It's a different approach because we look at the averages. We don't look at the individual.
Okay, got it. Thank you.
Okay. There are a lot of justification for using Shannon entropy. As I mentioned before, it's least bias because only the information that we impose is used, and we know exactly, even if we put assumption, in terms of the constraints. We can still test it, but we know there is no implicit assumptions. It is also based on a very nice set of axioms, but in addition, it also based on two wonderful theories that are related. One is the concentration theorem that is due to James, who derived the principle of maximum entropy that we were talking about. And the other one is large deviation, and the two, of course, are related. And you can think about it that actually those two derived from earlier work of Einstein when he did his work on fluctuations. So I'll show some motivation and think about it about those as large sample motivations. It's not axiomatic motivation, it's large sample. What happens if, for example, we played the game not 10 times, but 100,000 times? Okay, so this is the idea of what I'm going to show now. So this is the same simplex, and here we just look at, for an example of on three cases, mean value 1.5, 2, and 2.5. Okay, and this is based on the entropy concentration theorem, and this is the heat map that basically the entropy concentration theorems put, in this case, it will be a 95 significance, so it puts a 95 confidence interval around the one with maximum entropy. Okay, so it will be basically, think about it, if you have 95 different samples, it tells you where would you find their solution, and on average, and you see that the entropy here is much higher, but think about it as the confidence interval from here to here, for example, around each one of those. So when we only have 10, we played the game only 10 times, so the confidence interval, as one expects, is very wide. Okay, now this jumps to 100 games. 100 games, it's still not a lot. I mean, it converges extremely fast. Look at the confidence interval now around this point. It's very, very high, but remember, this is a 95% confidence interval. We can't do 100% confidence interval. It doesn't make sense, because then it's the whole real line. And this is if we do 1,000. So you see that the principle that we showed, even though I said it also can be based on axiomatic approach, on philosophical approach, and so on, it also has wonderful large sample properties. I can do the same thing looking at large deviations. Large deviation tells us the probability that we observed in reality a solution that is far away. So large deviation deals with a typical set or a typical probability. So what is the probability that you will find a solution in the atypical set? And so if you think of the maximum entropy solution as the typical set, it tells you what is the probability that it will be far away. This is if n is equal to 10, and you see again the heat map, the probability is non-zero here, but n equals only to 10. Now, as we increase it to 100 like before, you see that basically all of those, the probability here is practically zero for all practical sense. And then if you increase it again, it's another to n,000. You see again that all of this region, the probability that you will find a solution here, even though it could happen, it's extremely low. So now we provided a number of motivations for this approach. Last, I want to comment very fast because I don't want to run out of time, because I want to get to some extension and examples. This is a way because so far I talked about it as a constraint optimization, but remember, constraint optimization, if you have a lot of parameters and a lot of constraint and it's nonlinear, can become very complicated, not just statistically, but also computationally. But the nice thing here is that we can convert the problem to what I like to call a concentrated or a dual, which will be unconstrained optimization. A dual in the sense that it goes from the probability, it goes from the parameters of interest are the probabilities. So it goes from probability space to the Lagrange multiplier space, okay? Remember that Lagrange multiplier is what we call lambda, is always going to be much, much smaller than the parameter space of the probabilities, especially for more general, bigger problems, because the dimension of M always going to be much, much smaller than K. And then also once you convert it to the unconstrained, then it becomes much more efficient statistically and also computationally. And I'll skip this graph. This graph just tells us something about the relationship between the primal, the constraint optimization, and the unconstrained. So the basic idea here is the complexity here is not complexity of the data, it's complexity of the model. So the dual model, the concentrated model, is much simpler. It has much smaller, exponentially smaller number of parameters. It's efficient, and also it's from computational point of view, it's much more efficient. I'm going to skip this, but I'm going to use the picture. This is what is called the generalized entropy function, and the generalized entropy function include, and there are a number of those, the Renier, the Tsallis, the Kreiserid, and many others. But what it means is that it includes the Shannon entropy as a special case. However, one has to choose, you cannot estimate it, a certain free parameter, okay? But the reason I'm using it here, because actually under the generalized entropy function, one can basically specify almost all of the classical statistical methods. And I want to show basically that under this approach, we can generalize it and we can investigate and compare different approaches based on the decision function. So to remind you, this is the same simplex we had before, and this is the Shannon entropy, what I call the locus of optimal solutions. And now I'm changing the objective functions, and I'll define those in a minute, and to show that each one behave differently except one point. That's why I call it the center of gravity. Everything has to go through the center of gravity, which is the place in a simplex where all the probabilities are equally are equal, 1/3. And this is just mathematically, you know that this will be the case where whatever the decision function for this problem, when you have mean value, the correct mean, the fair mean in this case, then all of the solutions will be the same. So this is the only place where they converge. So to see the differences, this is what is called the empirical likelihood. It's this here. It's the closest to Shannon, but it's still different. This is, as expected, the linear model, least square. And those are some higher level entropies, like the Renier entropy of different orders. So you see that the choice of the decision is really important. And what in traditional econometric statistics we call a likelihood function is the joint choices of the decision function and the specification of the constraints, the structure of the constraints. I'm going to skip this because I want to get to the example, but this is the case where we have priors that are not uniform to show that, of course, it will affect the solution. And then we can do the same thing here we can introduce non-uniform priors, and then use under this approach, we can actually apply it using the least square, using any other approach. But again, you see that the each one will give a different set of possible solutions. So of course, it's important when we do any analysis and any modeling to think, okay, what is the decision function that we use? So I jumped over the other things a bit fast. I apologize, but now I want to generalize it to real life. Now that we have the framework, so the thing here in life, basically, we have some uncertainty and misspecification problems. It's called usually ambiguity and uncertainty or misspecification. And now I want to extend the model, the classical maximum entropy model, so it can accommodate for all of those possible uncertainties or deep uncertainty. Okay, so the idea here is to basically specify the constraints as flexible, because I don't really know the model itself. So I want to put, or the theory, so I want to put a little bit uncertainty about the model itself, and this will account for all possible uncertainties. And then I accommodate for this. I don't force it to hold, but I have to accommodate to this in case there is some uncertainty. And in this case, the basic model becomes, let's start with the constraints. So the constraints will be flexible. So it means that there will be uncertainty, additive uncertainty on top of each one of the constraints. There will be normalizations. But now I have to handle the uncertainty somehow. So I introduce here in addition to the entropy on the main signal of probabilities of interest, like the P's that before, I introduce here basically the entropy on the uncertainty, which I call W in this case. Okay, so this is the basic idea, and we can look at it graphically. So graphically, one can say that I can, in this sense, that here is some noise around this constraint, because whoever, if I know that instead of knowing that it's for certain y2, certain value, it is some other value with certain uncertainty. I call it here epsilon. You can think about it with a priori means 0. And this is the gray area here, okay? And if we have, and this is another example with a bit smaller uncertainty about another constraint. So what will happen with the constraints, what this picture shows us, and if we have uncertainty, if the constraints are flexible, we will be less certain about them. So the solution will move toward the center, because remember, as you move here, the level of uncertainty increases. So if I didn't have any uncertainty, this will be the solution. But if I have uncertainty and I have only one constraint, then the solution will move to a higher level of uncertainty, closer to a uniform distribution. Uniform distribution in information theory, it's the maximum uncertainty. Different the Bayesian, but this is the way it is defined here. And the same thing here, you see, if you have some ambiguity, some uncertainty about this, the value of this constraint, or maybe the behavior, maybe the constraint is a bit nonlinear, but I put it as linear, then because it's more flexible, the solution will go and become at a point where it has a higher level of uncertainty. Of course, it makes sense. So now let's look at a first example. So to see how it works, and then I move to some empirical example if we have time. So think of this is the story here. We have basically played the same die, because the same die, one thing about the same population, 2 times, okay? One time it gave us a mean of 1.5, which is here. The other time it gave us the same die. It has to be the same die because we want the probability distribution of this die. The other time it gave us 2.5. Okay, so those are supposedly contradicting solutions, correct? Means, because if it's 1.5, okay, it means that the solution has to be, and you have one constraint, so the solution has to be monotonically decreasing. If it's 2.5, it's monotonically increasing, as we can see here. So how can we reconcile it? Well, in the classical world, or statistics or whatever, we can reconcile it if we assume something that we know, and we can say, well, for example, this sample, the second sample, is it's twice as large, say, as the first sample, and then we will assume that there's less uncertainty here, so we can give here a different weight for the sample. So we'll give this 2/3 and this 1/3, and then we will reconcile those values, okay? However, this is based on assumption that we don't want to assume. So if we take the approach that we just talked about, allow for flexible constraints, so now think of the following story. So this is the first sample, which is smaller, okay? 1.5, this is the mean, and the dots on the white area, all the dotted area here, all the way here, is the uncertainty that we add to the constraints. Remember, now we said that we have flexible constraints, so it will be the constraint with uncertainty, possible uncertainty on both sides. Of course, it seems like we added more uncertainty here, but it's just because nothing outside the simplex is interesting for us. So of course, just this part makes sense. And we're doing the same thing for the gray area. So this is the sample that we have twice as many observations. So we trust it more. We put smaller level of uncertainty. And by the way, either theory or empirical evidence tell us those bounds. I will skip it for now, but the bounds will come either from theoretical argument in some cases, or if not, they will come from empirical evidence. So this is the uncertainty for the second sample, okay? And where does the solution have to be? The solution has to satisfy, remember, the solution has to satisfy both constraints. So in this approach, basically what it means, the solution must be, is what I call here the set of visible solutions in the dark gray area that includes all of the dots here. It's the place where the uncertainties, or the region where the uncertainties of all of the constraints, in this case 2, intersects. Okay, this is because remember, we want both constraints to hold. So this is the place where both constraints hold, or at least the uncertainties that are associated with them. You know, in practice, when you think even of simple least square, it's very much related to because you know the regression line or hyperplane goes in between all of those observations, but here it's much easier to see. So now we can see that the solution is this is what the solution is. The white circle here, and the black one here is the solution. If I would assume that basically I just arbitrarily, or not arbitrarily, based on what I said before, a ratio of 2/3 and 1/3, aggregate, get the mean value of the mean. So I impose assumptions that I can't really validate because I don't have this information. Now, so this is a very simple example, but it represents the case that we often have information that could be a little bit or seemingly contradicting. So, Greg, I think I have about 4 minutes. Is it true, or you want me to stop here?
Yeah, you do.
Okay. So let me go fast and look at. I'm going to look at actually one empirical example. I'll look at this one, and then I will stop. I have other examples. You can see some of this. I mentioned it then in my book's webpage, and in my book I also have a lot of examples. So this is example a bit related to the question that was before. So think about the idea that I want to infer the strategies of two firms that compete one against the other. Okay, so this is an empirical example. So this is the case of United versus American Airline, and I want to get their mix strategy because it's not pure in the sense that there is more than one possible strategies. So here is how it goes. So you think American versus United, and this is in routes where they dominate the market, where they have the biggest market share. So I can assume that those two dominate the market, so they play a certain game. And so the issue here, okay, how should I specify the constraints? There are the data that one can use, which is easy to use. You can construct the demand, the cost, and so on, but also the strategy. So the assumption here is that they play a certain type of Nash equilibrium strategy. Okay, so what one can do from economic theory or game theory, derive the Nash equilibrium conditions. Now, this is complicated a bit because the Nash conditions are quite nonlinear. They have inequalities and they have equalities. It's a whole mix, and it's conditional on what the other firm does. So you derive this from theoretical arguments. You allow for some flexibility, meaning additional uncertainty on each one of those strategies. You introduce the data, basically, and then you optimize. So the optimization will be the Nash conditions plus some uncertainty, plus some other information on the demand and cost, okay? And also with some additional uncertainty. And then you maximize the entropy over the parameters of interest, which is the mix strategy, plus the entropy of the uncertainty about all of the constraints. And this is what you get here. Now, in classical statistics, econometrics, you cannot really do it. If you look at the games there, they're usually reduced to a small number of possibilities. But this gives you the whole distribution. So, for example, let's look at two routes, say Chicago, Wichita. So this will be the gray line is American, you see, with two peaks. But this is basically, this is the price fare per passenger economy class. And this will be the Chicago, Wichita United route. You see, it's very, very different. It dominates to the right. So they have much higher prices and again, two peaks. And this is the Chicago Rochester this is for United, this is for American, so they are closer together, yet still in this case American is to the right, it dominates and it has on average higher prices. So this is just an example of what one can do. So basically what I did here, and I'll stop here, is introduce the very, very fast the idea of information theoretic approach. I touched a lot in the beginning about explaining the basics via a very simple three-sided example, and then generalizing it to some ambiguity, which is reality when we work with complex systems. And then I had time to show just one example. Thank you.
Yeah, well, thank you very much. Let me ask you just one question. For most applications, I think, The constraints are things like differential equations. They are, well, like the game theory, game theory is the constraint, which is a pretty elaborate constraint. Or if it's like an image problem, it would be the structure of a convolutional neural network, which is roughly speaking the structure of human vision. That's the constraint. How do you incorporate those very complicated sets of constraints?
So image reconstruction, for example, and I did some image reconstruction, and this actually approach works really, really fast. And image reconstruction, you're right. You just work from the image to itself, basically, and it could be many, many pixels. You can, so there, for example, I specify the constraint. So you can, it depends on the problem, but one informative piece of information there will be the correlation. So, for example, you assume you can exponential decay in terms of the correlation. So, especially in image reconstruction, correct? You assume that nearest neighbors could be more similar than farther away neighbors. For example, if I reconstruct a face, okay. So points on the nose, I mean, information around this point on my nose would be more informative here than a point right here in the other part of the face. So this is one piece. And then the other parts that to do it is you can look at the aggregated level. So I looked at the moments, basically, of the image. And you can look at horizontal, you can look at vertical moments, you can look at diagonal moments together with correlation. Those were the constraints in this type of problem. So you're right that it's very problem specific, but it's all the basic falls within the same framework of trying to specify the constraints to capture the information that you think is the most important.
So I guess, so what you're describing, I'm going to go to subsurface geology because that's the closest to the constraint you're describing. So kriging is a classic technique there, which literally says, the composition of the subsurface on nearby spots is a thing, Gaussian correlation like function is close, more correlated than faraway things. And more sophisticated things then would say, I'm going to do a simulation of how subsurface geology is formed to begin with, and that's the possible outcomes of strata showing up. That's going to be my prior. That's a much messier prior, but it's just far more detailed and constrained. So how would you incorporate those, well, essentially simulations as your priors as opposed to the simpler correlation functions?
Okay, so one thing is when I think about priors enter in the objective function. So then you switch it from, say, Shannon entropy to the Kullback-Leibler, because priors, you see, the difference is that constraints have to be satisfied explicitly in the optimization. Priors don't. Priors help you, but the data and the information can take over the priors, basically. So when I think of
constraints is probably a better term for what I have.
So I think what you had in mind were the constraint. I skipped because I ran out of time. I apologize. I didn't show some example where, for example, for election, if you use priors on individuals, which can be constructed from the previous samples, you get better prediction. But those are priors. Yes, you are right. I mean, it's the constraints are the toughest issue, and this is why it's really problem specific. I talked about it in general way. Example from simple economics, if I want to look at the distribution of welfare, for example, or the GDP, then the constraint shouldn't be the arithmetic mean. They should be the geometric mean, because we know from zero in classic that because it's a power law. So theory, so when you work on a specific system, you know exactly how to create it, but you're right, it's complicated. And even the image reconstruction answer that I gave you, it took time to come to this, to understand that if I look at, say, the moments, horizontal and vertical, and the nearest neighbor correlation, then it gives me a good reconstruction of an image. So it's kind of And sometimes it's a given with image, it's easy. You just, you switch your constraints a little bit until it gives you the image that you want. But one thing, if you go, I think it also holds for the problem that you mentioned. Think about it, once you convert it to its dual concentrated, it will be very, very efficient. In a way, with image reconstruction, at the time that I did it, I think maybe 12, 13 years ago with this approach or similar approach, the idea was, for me, was speed. Because I didn't care really if the reconstruction had some stains in it. If there is a stain on my nose, it doesn't really matter. It's just like I put some blue color on my nose, you can still recognize that it's me. So for me, it was the speed, the efficiency of the computational efficiency. Because so unlike neural net and Bayesian net and all of those that you get best reconstruction, it takes a long time. This, if you think of what we talked before, because here you have a lot of parameters. If you think of all the pixels, but you transform it to the Lagrange multiplier, it will be basically just the number of rows and columns. It's exponentially smaller, and there are no. It's a simple optimization, so it's very efficient. But going back to your question from geology, it could be more complicated if the constraints are somewhat nonlinear.
Okay. And it sounds like the answer to my question is really that your emphasis is on these simpler constraints, which have more, less doubt about whether they're valid or not, as opposed to these complicated simulations. And therefore, they're also a side effect is they're also far more efficient because you have far simpler, dynamics in your constraint solver, right?
Yes, if I can do it, it's good. But the example that I just showed with the mixed strategy, I did not convert it to, for example, to the dual. It's because those, it's very complicated to get into the dual of the notch. So there I had to use the full optimization. It still, as you see, it still works. Not always you can command it, but the good thing here, and we didn't really get to this much in the discussion, is that what it does, it provides me with the approximate model, or I call it approximate theory. It's the closest possible theory, given the information that I have, to some kind of an absolute of the correct theory, or the true theory that I will never discover anyway. Okay. So it will give me the closest possible, or I call it approximate. Another example that I had in the talk, maybe if we do it another time, will be a Markov process. So usually people look at the steady state solution or transition probabilities, but it's under very strong assumptions. Is there really a steady state solution? If you don't look at 10 periods, or in your case in geological terms, there's no steady state. Things are moving all the time. Right. So we need this additional uncertainty to give us this approximation, basically.
Okay, that makes sense. Yeah, well, thank you very much. It's fascinating.
Thank you.